So here we're going to look at current in DC and AC. So DC again stands for direct current, AC stands for alternating current. In A, we're going to have a simple little circuit here with doing something, it doesn't really matter, and you're going to have the direction of current drawn, and it's going to be 5 amps of current going through that wire. However, in B, we see that the direction of current drawn is the exact opposite, so essentially the arrow is going in the opposite direction, and the current is given a negative sign. A and B are exactly the same from a mathematical standpoint and from a circuit standpoint. So in the future, it's very important when you're drawing your test and writing your tests up that you draw in the directions of current so that you don't get them wrong. So for instance, let's just say we had the same circuit here, the current going down, the blue arrow going down, and a negative 5 amps. That's not the same as these two. That's the opposite. So that's an incorrect answer. But both of these are the same. As long as you keep your arrows going in the direction that you're doing math and you follow the same conventions, you'll come out with possibly a negative 5 amps. But that's, again, it's a correct answer. And the top right, if we look, we're going to look at some of the responses from current over time. So for direct current or DC current, essentially that's saying that you're always going to get the same amount of current out of the system at any time as long as the system's plugged in. So DC current you can think of as like a cell phone charger. That's always going to output, or your computer, your USB is an even better example. Your USB always outputs on a laptop around 100 milliamps of current. That's constant. It doesn't change. That's what's good about DC current. It's 5 volts, which we'll talk about later, and about 100 milliamps. Some of the bigger, newer ones have 200 or 300 or more. But generally, from a computer standpoint, it's a 100 milliamps. But it's flat. It doesn't change that current output over time. It will always be the same, 100 milliamps. Or if it's a 200 thing, it will always be 200. For alternating current, we have a slightly different system. So alternating current, which is diagram B on the right, is current over a function of time, current per function of time. And alternating current oscillates up and down, following a sine curve or a cosine curve. And the most common thing of alternating current is actually the current that flows through your house. The current that flows through your house is a 60 hertz signal, which means essentially 60 vibrations per second. And that essentially forms the wavefront that you're going to see oscillating up and down. So it's going to have a positive, a 0, a negative, a 0, a positive, or sometimes for some other alternating currents, you can shift them up all into the positive or shift them all into the negative. But the point that's important is it's a changing current. It's alternating, and it's alternating in a pattern. The one below that, C, is decaying current. So decaying current is actually interestingly used many, many times. You can actually see it in the charging of the capacitor. I know it sounds counterintuitive because you would think as you're charging a capacitor, the current would be increasing, but it's not. If you remember the capacitor equations, which we'll look at again, as you're charging a capacitor, you have less and less current going through. As more and more charge is built up, less is allowed to flow through it. Again, we have below that a rising charge, so essentially more current is flowing through the system as a function of time. And then in E, we start to get some complex currents, this one is a damped oscillatory current. And these can be combinations of different signals or combinations of different power or current that goes through. It depends on what the system is. But essentially, the damp part means it's being controlled in some method, so it's not going out of control. The signal isn't getting larger and larger and larger. And the oscillatory says that there is some kind of wavefront that goes through. There's some kind of predictable pattern. This is one of our first examples that we're going to look at, and this is for charge transfer. So the question it's asking is, given the current as an equation of time, and then two different parts of that equation. So the first one, that the current as an equation of time equals 0 if t, or time, is less than 0. So that means anything from negative infinity up to 0, the current is going to equal 0. And that the current at any given time after 0, including 0, but after 0 as well, can be explained by the equation 6e up minus 0.2t amps. The A is for amps. It's not actually a variable in the equation. So it's going to ask us what is the Q of t, or what is essentially the general equation that we're going to use to be able to solve this. And then for B, it's saying what is the net charge. And the net charge would be at these two given numbers, what is the net charge? What is the total charge in between seconds 1 and 2? So A is going to give us essentially our equation that we're going to use in our essentially our integral solution, and B is going to solve that integral with specific data points. And then what we're going to do with this is we're just going to plot them out too, just to kind of look at what's going on here for a charge problem.